Hello guys, welcome to my channel WinChem. Today we are going to see electrochemistry, which is highly useful in all the problems. Okay, so we are going to see only a mind map and the formula which is discussed in the electrochemistry. Easily we can go through it. Okay, what and all is there in electrochemistry? In electrochemistry, we can segregate that as galvanic cells, electrolytic conductance, and its applications. Okay, what is galvanic cells and what is electrolytic cells? The galvanic cell is a cell which converts chemical energy into electrical energy. That is galvanic cell. And electrolytic cell is just reverse to that. The electrical energy is converted into a chemical energy. Okay. And what is the electrolytic conductance? Electrolytic conductance, what is that? That is the electricity is conducted in a substance. Okay, substance which conducts the passage of electricity, and its applications we are going to see. Next one, galvanic cells. In the galvanic cells, what are all the topics under the galvanic cells? Okay, first one is Daniell cells. The galvanic cells and Daniell cells, most of them both are similar only. It's nothing different into that. Everything is similar only. And off-cell reactions, we know Daniell cell, that is a redox reaction is taking place in electrolytic reaction, in electrolysis. That is the Daniell cells. In this, no, redox reaction is taking place. Both oxidation and the reduction reaction is taking place. In the Hopf reaction, what all the types of Hopf reactions are there? Metal ion and metal amalgam ion, gas electrode, redox electrodes, and metal insoluble and soluble salts with a common ion. Everything is this all like that. We are segregating the types of Hopf cells. Okay. With the help of the salt bridge and its uses, or no, what salt bridge and its uses. With the help of the salt bridge only, we can convert the chemical reaction into the electricity. Okay, chemical reaction is converted into electricity. And here the third one, potential. Potential is we can separate it as cell potential and a Hopf cell potential. What is cell potential? Cell potential is the potential difference between the redox reaction, that is between the reduction and the oxidation. Okay, in this cathode is the reduction reaction is taking place in cathode and the oxidation is taking place in the anode. Okay, always you have to write E cathode minus E anode. This is the formula. E cell is equal to E cathode minus E anode, where whatever the EMF of the reduction we have to write first and minus of the E anode, that is oxidation. And the Hopf cell potentials. In that Hopf cell potential, the standard hydrogen electrode, everything is comes under the Hopf cell potential. Okay, and the next to that, Nernst equation. Okay, Hopf cell potential and cell potential, both is there. If Hopf cell potential, you see that EMF is equal to standard EMF plus 0.059 divided by n log oxidation state by reduced state. Here, if you write oxidized state on the top, it should be plus. If it is reduced state on the top, it should be minus. You see the formula properly and write it according to the requirement. Okay, a cell potential. The same way, this is also cell E cell. The same thing here. The metal is there. Here, a cell. You are taking the complete one. This is only half. This is complete one. Okay, complete cell reaction. E cell, E naught of E cell plus 0.059 divided by n log of reactant divided by the product. Okay, the relationship between standard cell potential and the Gibbs free energy. What is the relationship between? What is the formula? Only I mentioned all the formulas. This is sufficient to calculate all the problems. Okay, that's why I'm mentioning only problems what are all included in the electrochemistry. That is, I mean, I'm going to go through it. So it's easy for us, whomever it is seeing the electrochemistry. No need to think about too much. If you know these are all the things, if you are familiar with these words, you can come across. You can able to do all the problems. So standard Gibbs free energy is equal to minus NFE cell. Okay. F is the Faraday's. Okay, Faraday's. N is the number of electrons. Okay. Here the relationship between the standard cell potential and equilibrium constant. The K is the equilibrium constant. Here, see here, instead of this, we can make it as a K, the equilibrium constant. 0.059 divided by N log K. When E cell is equal to 0 means E cell, when E cell is equal to 0, E naught cell which is equal to 0.059 N log this one. This one is equal to K. Okay, K. This is the relationship between standard cell potential and Gibbs free energy, standard cell potential and equilibrium constant. The next one, electrolytic cells. The electrolytic cells, we can divide this as a Faraday's laws. First laws and second laws. The first law is W is equal to ZIT. Z is equal to gram equivalent by divided by Faraday. F, that is 96,500. And second law, W1 by W2 is equal to E1 by E2. We can write it as W1 E1 is equal to W2 by E2. In a cross way also we can write it. Okay. That IT, instead of IT you can write it as Q also. The Q is a charge, that is current into time. That also you can write it instead of IT. Okay. That is also first law only. And what are all the products of electrolysis is there? Preferential discharge theory and nature of electrodes and over voltage, everything is comes under the electrolytic cells. And how to construct the electrolytic cells and what is the mechanism of electrolysis, everything is under electrolytic cells. And the next, electrolytic conductance. Already said, the substance which conducts the passage of electricity, which allows the passage of electricity, that is electrolytic conductance. Here we are comparing with the metallic conductors and electrolytic conductors. Both we are comparing in this chapter. And what are the factors which affects the electrolytic conductance? Ionic interactions, that is electrolytic conductance which is inversely proportional to the ionic interactions, solvation and viscosity. But it is directly proportional to the temperature. Okay, these three are inversely, and the last factor, which is temperature, is directly proportional. And Kohlrausch law is also comes under this electrolytic conductance. Okay, for what purpose we are using this? This is the molar conductance. We are finding out the molar conductivity of the weak electrolyte. And here all the electrolytes are a summation of all the electrolytes. By the help of the summation of all the electrolytes, we are finding the molar conductivity. Okay. What and its application? In its application, we are use these formulas, that is degree of dissociation and equilibrium constant. With the help of the equilibrium constant, we need the degree of dissociation. We are substituting with the help of the degree of dissociation. We are finding out the equilibrium constant K, and solubility S. Solubility S, how we are finding out with the help of molar conductivity. Okay, molar conductivity. If you know the molar conductivity, then only we can find the solubility factor. So everything is under application of the Kohlrausch laws. Okay, and the properties of electrolytic conductance. What are the properties is there? Resistance, conductance, resistivity, conductivity, molar conductance. Resistance means R is equal to rho L length by area of cross section. The rho is the resistivity. We can say rho as a resistivity. It's a ohm. Unit is ohm. And conductance is the inverse of the resistance of conductance. Okay, so area of the cross section divided by its length. Okay, this is the constant. Okay, this is the kappa. So G is the conductance symbol is G. Conductance symbol is G. So inverse, that is ohm. This is ohm. This is ohm inverse. Resistivity is rho. Already said this is rho. So rho is equal to, if you know the resistance, you can directly write the resistivity also. The rho is equal to R into A by L. So area of the cross section divided by length. So in the same way, conductivity also we can write. Conductivity is K. This is conductivity. Kappa is equal to G length by A. So this is also inverse of this. If you know these two you can write it. The molar conductance. Molar conductance is equal to kappa into V. And Debye-Huckel-Onsager equations are the last one. Okay, this is also molar conductivity at a given concentration, which is equal to molar conductivity of the initial concentration, that is 0 concentration minus A is a constant into root of concentration. Okay, these are all the factors which comes under, which are chapters which comes under the electrolytic conductance. And the next applications. What is applications? The two applications are there mainly, that is batteries and corrosions. The batteries, three things are there: primary cells, secondary cells, fuel cells. Primary cells, what are all the batteries are there? Dry cells, mercury cells. The dry cells, these are all the cells which are used in a clock, everything. And the mercury cells, the toys and what are all the batteries which is used in the mercury cells. And here the secondary cells, lead storage, nickel cadmium cells. These two are secondary cells. These are all comes under the application factors. So if you know these four chapters, it's very easy for you to know the electrochemistry. Thanks for watching. Subscribe my channel, click the bell button and share to your friends.